So today, Dario and Garcia will continue with the tutorial on school of finite structures.
Thank you, Antonio, for the presentation. Thank you, everybody, for coming here. To planning to come here, that's already a thing, and also to actually do it. So, okay, I'm going to continue what I was talking about yesterday. Just to remind you, we were talking about neutral products of finite structures, and we were talking about how to prove that a structure is easier to find or not. And remember that the idea is to have a clear axiomatization of the structure that we want to see if it's defined or not, and then try to realize that axiomatization by a neutral product. That was one way. And the plan of today, is divided in three different things. So the first one is going to be talking a little bit about applications of pseudo-finite structures in combinatorics, which are probably examples that are known in the last 10, 15 years. Then talking a little bit about cardinalities of definable sets in neutral products of finite structures. I'm going to say a few words about this. And then the third part will be coming down back to the finite structures. Okay? So we have been talking about taking a class of finite structures, take neutral product, properties of neutral product. Now, after we talk about non-standard cardinalities, we will try to go back to the finite structures and see what can we say. Okay. So let me just start, and this is the first natural question that I didn't answer yesterday, right? Why it would be good, useful, or whatever to study pseudo-finite structures? Okay, and there are probably a couple of key themes here. One of them is that well, it is interesting. There are limits of finite structures in some way, but they also have been proved to be useful in combinatorics, or what I like to call asymptotic combinatorics, right? If you have a class of finite structures and you want to prove that there is certain behavior, certain structural behavior on the structures in the class, what you can do is look at the limits, look what the limits say, and then try to go back. This is more or less the idea of this. And basically, there are a couple of things here. So the first one is the fact that if you take an neutral product of finite structures, then in the finite structures, you can talk about the size of the definable sets. You have the subsets of the structure defined by a certain property, and you can ask how many of the elements satisfy such property. That's what we call the cardinality of the set. But if you pick up all these sizes and you go to infinity, what you're going to get is a non-standard real number. So what you can do is take the neutral product, take certain formula, certain property. Imagine, for example, if we're working about groups, you can ask, for example, which of the elements are divisible by 2. Like we're talking about groups. And then there might be some of them are not, and then you just take this thing, which is going to be the non-standard real number given by the sequence of such finite cardinalities. That's going to be a non-standard real number, but as we mentioned yesterday, well, that is still a ring. You can still add the cardinalities, multiply them, take powers, do whatever you want with them. So you can treat this as an actual natural number because it will have many of the properties that natural numbers will have. And with that, you can define several things. One of them is, for example, a counting measure. You can basically take the counting measure of the electronic structure, which is basically the size of D divided by M. That's indefinite structures. If you take the non-standard limit of those, you're going to still take D divided by M, which is going to be a non-standard real number. And it's going to be between 0 and 1 if it is a subset of M.
Dario?
Yes.
M to the N to be more precise, like if D is a subset of M to the N.
Yeah. So we're thinking about the first line. I'm thinking, for example, if you imagine D a subset of M squared, for example, this pairs that satisfies every condition, then you can take here the non-standard cardinality, just the size of it, and then go to the limit. And here in the second bullet, I'm assuming that this is a subset of M, but it can also work with any power also.
Can I also?
Sure.
If you do the other way around, so you take D divided by M on every finite set, you just take the root limit to that. You get the same number?
You will the same number, just take this number.
Yeah, when it takes okay.
Yeah, it's precisely the same. So you can take non-standard real number d divided by non-standard real number n. There's going to be a non-standard real number between 0 and 1. And a property of the non-standard reals, especially the bounded ones, is that there is always a real number that is infinitesimally close to it. Okay, that's what is called the standard part. And then when you do this, you get a natural probability measure. And if you get a natural probability measure, well, this is finally additive. With a little bit of work, you can show that it can be uniquely extended to a sigma additive probability measure. And then you can use all the techniques that you prefer to use for measure theory. You can take expected values, you can do some function analysis, you can do a lot of stuff. You have a lot of what I like to call tools in infinitary mathematics to work with those products. Okay, so this is the way to get the measures, but also there are certain kind of numbers which look a little bit weird. We're gonna spend more time talking about them tomorrow. But the important thing about this is that these act like dimensional operators. They have certain properties that one would expect for dimensional operators to have. They don't take values in the natural numbers. Sometimes they do, sometimes they don't. In general, they don't. But it is still useful to, they are still useful to detect like jumps into how big a set is, in the sense of, if you think, for example, philosophically, what is the difference between something of dimension 1 or something of dimension 2? One of the things that one would like to say is that there are infinitely many things of dimension 1 inside the world of dimension 2. This is more or less the idea that is going to be behind this. So probably the actual numbers that it takes do not matter much, but actually the important thing is when they change values. Okay. And once we have these new tools, then we have actually like a sort of template to prove things in asymptotic combinatorics. So imagine that, for example, you have a class of finite structures and you want to prove certain things, certain property that I'm going to call P. Okay. And we want to show that every structure that is sufficiently large, still finite, but sufficiently large, satisfies property P. So a way to prove this is to say, okay, first find a way to define P in a first order fashion. Okay. And this is a little bit weird because it could be that P is already first order defined and everything was well. It could be also you need to add certain things on the language, like certain approximation properties or whatever, but still, the idea is to make it first order. Because if you want to show that every sufficiently large structure in C satisfies the property, you can assume by contradiction that it doesn't. And that means that for any possible cardinality, I can find large, structures in the class that are bigger than that possible cardinality that do not satisfy the property. This is what we call the sequence of counterexamples. Okay, so you collect all these counterexamples and then you produce an ultra product. And the ultra product is, in theory, is going to be the ultra product of these things. Therefore, it will not satisfy the property, right? Because of wash, if we did everything in a first order fashion. But also, the ultra product is going to be infinite. So we can use what I like to call tools in infinitary mathematics in the product to produce a contradiction. Okay, so this is a general strategy. Of course, it depends on whether the theorem is actually true or not. There are many variants of this, but I like to mention that this strategy has been used in many contexts to prove several theorems in combinatorics. So, more notably, more recently, Goldring and Dausner gave a proof of Semmelweis regularity lemma, which is a lemma in graphs. And it's also, I guess, Henry Dausner by himself, he also used this kind of methods to prove the Semmelweis theorem in number theory, which says that every subset of the natural numbers of positive Banach density must contain arbitrarily long arithmetic progressions. So this is the kind of results that one can get. And the way Dausner proved it was, okay, take this subset and just take finite bits of the index. Okay, so just take the interval from 0 to n, make n go to infinity, take the ultra product of the possible counterexamples that there are, and then once you're in the ultra product, that you can use all the magic of measure theory, try to intersect, try to bound measurable sets, etc., until you get a contradiction. Okay, so this is what Goldring and Dausner did. Krzyzewski had used also this kind of construction to prove what people call the Feynman theorem for non-abelian groups. So Feynman theorem is a result in additive combinatorics for abelian groups, and he proved a version of it for non-abelian groups that was later reproved with different methods by Green et al. And Juliet. Also, the same turnstile uses this kind of approach of trapezoidal finite fields to prove what he calls the algebraic regular dilemma, which is about graphs definable in finite fields. And I'm going to talk a little bit more about this tomorrow, but basically there are proofs that using stability as a tool in infinitary mathematics have proved the Einstein potential for several classes of programs. Okay, so talking about any of these methods will take a long time, and that's not the purpose of this course. So I would like to point you to this nice book about like how different methods in ultrafilters using ultraproducts have been used to prove results in combinatoric exam number theory. Okay. However, I'd like to mention a small example. So I'm gonna use this strategy to show a term that probably most of us know already. Okay. I'm not claiming that this is gonna be the most beautiful or the best proof around system. That would be too much for me to say. I just want to point out how to use this strategy. I mean, in a very easy example that I can handle. So let me recall the term that actually Christina mentioned yesterday in her talk. So Ramsey's theorem. This is going to be a very easy, like two-color version. So let me just phrase it in different ways. And the Ramsey's theorem says, okay, fix a number k, natural number. There has to be a number n, usually bigger, such that whenever I take a finite graph of size bigger than n to the k, sorry, n of k, if it has these many vertices at least, then it contains a clique or an anti-clique. Okay, it's basically the same. So usually the example that people give is the Ramsey number of 3 is 6. What it means is that whenever you have a graph with 6 vertices, there's going to be a triangle. I mean, either three elements that are connected with each other, which is going to be a clique of size 3. Or two elements that are not connected with each other, which is an anti-clique of size 3. Okay, that's what we will call it yesterday the homogeneousness. Okay, so I have such theorem. I want to use this method that I mentioned before to prove it. What can I do? So first, try to find a first order, try to express the property in a first order fashion, but it can be actually expressed in first order very easily. I just say, well, there are k elements that are all different, and either they are all related with each other or not related with each other. Cool. Have you written first order sentence? Nice. Then I take a sequence of counterexamples. What would it mean for this term to be false? It means that there is a k fixed such that I find larger and larger finite graphs that do not contain any homogeneous sets of size k. Okay, so I take those counterexamples. I take a sequence of finite graphs, all of them satisfy the negation of this sentence. Okay, cool. I produce an autoproduct. So I take an autoproduct of these graphs. That's going to be with respect to a principal filter. So that's going to be an infinite graph that does not contain any homogeneous set of size k. Okay. And that now I'm going to prove that that is impossible. And because I have a lot of elements, in this case, the infinitary tool is one of the first tools that one sees, which is the big gap existing between infinite cardinalities and finite cardinalities. Okay. So I just start with 1 point, fix 1 point. So, and consider the relations with the other infinitely many points, right? So it might be related with some of the points and not related with some other set of the points. One of the two sets must be infinite. Let's assume, for example, I'm going to say red for not connected. So let's assume that it's not connected with infinitely many elements. And I'm going to call that set E2. Nice. Then I take the first point of that set, and I consider its relations with the other elements of the same set. It might be related with some of them, not related with some of them. Let's say, for example, that it's related with infinitely many of the sets that are below. So it's important that E3 is containing E2 as subsets. Okay. So I take the first point, I start continuing this process, blah blah blah. How many times do I do it? Just do it enough times. So it's going to be, let's say, 2k plus 1 times. Okay. So after 2k plus 1 steps, and I can do that because I always have room to do it. Well, there are either k lines that are red or k lines that are blue, meaning there is an anti-clique if there are k lines that are red, given by these points, for example. Or if k of the lines were blue, then I have a clique of size k. Another way I found that the ultra product must satisfy the sentence because of other reasons, and that's why most of the structures that we're studying must satisfy this approach. Okay, I know this is a toy example. This is a very weird way of proving Ramsey's theorem, but it's just to show like what would be the kind of strategy that we expect for these applications. Of course, this is much more easy than the applications that I mentioned. Any questions so far? No? Excellent. So let me now talk about the other part of the title of the tutorial. Right? It was called Model Theory of Pseudo-Finite Structures. And in order to say or to mention several of the results I'm going to mention today and tomorrow, I like to take a step and try to give a more like philosophical approach of how I consider things to be done in model theory. Probably some people might disagree, but I mean, in my experience, model theory have been a lot about like working with the dichotomy tameness versus wild in first order structures. What do we mean with that? What do model theories mean when we say something is tame or something is wild? It's just a feeling. Right? There is no clear definition. There are approaches, but there is no clear definition of what is it to be tame or to be wild. So we have what I like to call the quintessential example of a tame structure, right? What is a tame structure? Well, for example, the field of the complex numbers. Why is it tame? What are the properties that make it tame? Well, first of all, it is effectively axiomatized. You can actually enumerate in an effective way the axioms that are necessary to axiomatize completely the sentence that are truly complex. Okay, you have the field axioms. You say that the field is algebraically closed, meaning saying that every polynomial, every non-trivial polynomial of degree n has a root, and then you say that it has characteristic 0. And of course, these are easily many axioms. One can say, okay, probably something that is finally axiomatized is better. But I mean, still there is an easy way of enumerating these axioms, an effective way to enumerate these axioms. It gives you a complete structure, and not only that, but also the definable sets are somewhat easy to understand. So, for example, if we take a definable set with one variable, a property that can be first order expressible in the language of rings, in the complex numbers, that has only one variable, the set is either finite or cofinite. That's one of the main properties that is called strong minimum. I would like to say, okay, this structure, we can actually understand the definable sets, we can understand the theory. And on the opposite side, we have the quintessential example of a wild structure. Okay, the quintessential example of a wild structure is usually the ring of the integers. Why is it wild? Well, if we're comparing it with this tame structure, well, you cannot axiomatize effectively the theory of the ring of the integers. Of course, you can just say, okay, this is countable and just enumerate it, but it's not going to be effective in any way or completely in a reasonable way, let's say. And also, there are some things going behind that are making it very difficult to understand. In the sense, I mean, that make the definable sets very difficult to understand. Okay. So, for instance, this example here, if you understand the definable sets that do not use quantifiers, you are good. You are understanding all the definable sets. That's completely different when you go to this rank. You have to understand sets that are definable with quantifiers, and the problem with that is that probably you are used to it. Every time you alternate a quantifier, your property becomes more and more difficult to understand, right? Every time you pass from a for all to an there is, and then there is for all, then is difficult to understand. And if you don't believe me, well, you have to go back to analysis and say for all epsilon there is a delta, right? So this is the thing. Model theories, we use the terms tame and wild very informal. We just want to do a distinction between what we consider good model theoretic properties and bad model theoretic, well, not desirable model theoretic properties, let's say. And Shela is probably the person that has tried to attempt to classify these tameness and wildness behavior, and he defined what he calls the dividing lines. Probably we call it dividing lines, sometimes we find them. And so he defined these combinatorially defined properties, stability, simplicity, and dependent theories for NP, NP2, blah, blah, blah. And the idea is to distinguish through combinatorial configurations of definable sets, what 10 is and what wild is. Okay. In particular, in this context of simple theories, it defines what is called the SE rank, which is some sort of dimension that takes values in the ordinals and can be used to like try to provide certain geometry in the structures, even though it's defined in another way. And also, I like to point out this last phrase, which was, I guess, written by Van and Ries as an expose of Dario Fuchowski. So Fuchowski says, null theory is the geography of mathematics. That's what he says. But the point, what Van and Ries points out is that even if you have a wild subject, for example, number theory, sometimes the solution to problems comes to understand the tame part of it. Okay? And then that gives me this opportunity to talk about what could Fuchowski do with this geography of tame mathematics, even though he doesn't explain. Well, this is like a drawing of what we call the map of the universe. There's actually a web page where you can see more details on these properties. But in this map of the universe, what you see is, so there are these names I mentioned before, like some minimal, stable, simple, rosy, turbo, and blah, blah, blah. But the point is that these are all the properties that Shela has defined, and there is certain interplay of the properties. So for example, it is known that if a structure is simple and is NIP, independent also, it is stable. By the way, that's why you have this automatic. And it's also known that any simple and NIP is going to be NTP2, so this is why this space appears. And what you can see here in blue is just certain structures that lie in those properties. So for example, I was mentioning the complex field as the more tame of the structures. Then you get, for example, the group of the integers, which is stable, or the ordered group of the integers, which is NIP but not stable. And then here you have the ring of integers, which is supposed to be wild. So the more up you go, the more wild you are, the more left and down you go, the more tame you are. Doesn't necessarily mean that this is good or bad. It's simply the way we classify things. Okay. And for example, here, notice that I was mentioning the random graph yesterday, and also the products of finite fields. These are examples of simple and stable fields. And I know I haven't defined any of these terms. I will invite you to go look for yourself. I'm going to talk a little bit about stringing minimum and stability during these two lectures. Okay. Good. So what I want to do now is to say, okay, I have these nice monitoring properties. How do they tell me something meaningful about the classes of finite structures that I'm going to use? And for that, I'm going to talk about the non-standard kinetics of definable sets. So let's start with a question, very simple one. What are the possible kinetics of definable sets in classes of finite structures? Okay, that sounds like a very interesting question, but if you think for a couple of seconds about it, it's like, well, any possible finite kinetic, you can do it, even just with equality. Tell me you prefer size, for example, 20, and I just have a formula here, which is we uses several, probably 20 parameters that can define any possible set of size less than 20, right? Just by using equality. So even in the easiest of the classes of finite structures, you can define definable sets of arbitrary finite size. Cool. So this is probably not a good classification. Then what about saying, okay, if you notice what is going on with this formula is that if I want to define a bigger set, let's say something of size 100, I have to use more parameters. So in principle, I'm changing the formula all the time, right? So one can ask, well, what if you fix the formula? You fix the formula and ask for the possible sizes. What are possibilities? And then you say, well, even in the easy example of finite linear orders, you can find sets of arbitrary size. Let me show you more or less how it's done, although it's very, very easy. So, for instance, you have finite linear orders like this, right? They go bigger and bigger, blah, blah, blah. You take the neutral product, we know that the neutral product looks like omega plus some dense copies of the integers and omega star at the end. But let me just mention something about the sizes. I'm going to call this 0, oh, sorry, 1. Which is the minimum, And let me call this, so this finite structure has a size, certain size, I don't mind. Let's say A1, this is size A2, and so on, this is size A3, blah, blah, blah. That will give you something that is called alpha, which is a non-standard real number. And any possible size between actually 0 and alpha can be obtained in these structures by using the formula phi x y equals x less than y. How can we use it? Well, just take any possible element from the top. That's going to be, say, for example, element here, let's call it gamma. That comes from certain sequence of sizes, and then I just take the sizes in the book. Right? That's how I do it. So by picking this element, okay, at the end I'm going to have a definable set, always given by the same formula, that will give me any possible kernel, well, any possible non-standard kernel between 0 and alpha. Okay? So this is no use. At least we have to take into account two things here. One is probably I can only do it formula by formula. It would be too much to ask if I want to do it universally. And probably I have to take out certain examples that do not match the pattern. Okay. So my natural question then is, okay, first of all, if you have a class of finite structures and I can give certain characterization of possible kernelities, what does it say about the class? And vice versa. If you have certain conditions on the kernelities of the definable sets in the class, what does it say about the two products? Okay. So let's start with this first model theoretic condition, which is being strongly minimal. Let me just discuss a little bit about this. So I know this is usually defined in terms of theories that are strongly minimal. I decided to use structures here, but it's going to be equivalent. So structure M is said to be strongly minimal if, whenever I consider any structure that is elemental equivalent, meaning whenever I have a model that has the same theory as the theory of M, and I have formula in one variable, I take the definable set, and that set is either finite or cofinite, okay? Even if you use parameters. So if you have definable sets in one variable, that's either finite or cofinite. Examples of these structures. Well, we have, for example, the natural numbers with equality, because that's where the name comes from. So minimal is the minimal things that you can define with equality. And those are finite and cofinite sets. But also, you have this example of yesterday, this regular tree of branching equals to our every point has our neighbors. Those are strongly minimal theories. Also, this example yesterday, this is the same, it's elementary equivalent to the group of the reals, which is still defined also. Or this vector space F to the omega, the complex field that I mentioned before. All of these three are examples of strongly minimal structures, and some non-examples of strongly minimal structures. Some examples of non-strongly minimal structures. You can find these that I mentioned yesterday, which is countable set with an equivalence relation to infinitely many infinite classes, that's infinity, or the infinite tree that I mentioned yesterday also. Any model of the random graph is not going to be strongly minimal. And it's easier to mention why these are non-examples. So, for example, in the random graph, you pick a vertex, right? And you ask, what are the vertices that are connected with this vertex? Okay. Because of the axioms of the random graph, there's going to be infinitely many vertices related with it, and infinitely many vertices that are not related with it. Right? So this divides the set into two infinite sets. That's not a standard. Okay. That's kind of the thing here. Also, here in the reals, but you have the interval 0, 1, that's infinite, and the complement is infinite. Also easy to see. But I want to now explain a little bit what is going on in these lines. Okay. And what is going on in these lines is sort of like, let's call it epistemological, philosophical principles that one has in mind when he's starting model theory. So this is what these structures have, what we call trivial structure. This can be specifically defined, but it basically means that there are not many binary interactions between them. Like pretty much, if I want to take what are the things that are algebraic over one is equal over a set, it's basically taking what is algebraic over every single element of that set. There's more or less they look. So they look more like examples of graphs and this kind of stuff. these have what we call the vector spaces structure. Of course, they are vector spaces, but there is something that is called local modularity, and these structures are going to be examples of local modular structures. And this is a field. Well, it's a field. There is no quotation marks or anything. Here you have certain like structures that are given in terms of equivalence relations. Okay. Well, this one is actually an equivalence relation, easy. And this one, you can see, for example, if you fix a vertex, you can see the distance. I mean, the ball radius one set in this vertex. That's like a class of elements. There is a second class which is the ball radius 2, and so on and so on. You can like divide the structure into different disjoint sets that are all defined. It's more or less the idea when I say equivalence classes. The model of the random graphs, they are random-like, meaning that there is a random process going on. And these structures here, well, they have an order. So there are like random-like structures, order-like structures, this kind of stuff. Of course, this is very philosophical, but it's important to say also that it goes in the same lines as these things. So if you check at these examples, usually what happens is that the stable part is something that avoids randomness and avoids orderness. Okay? If you grow into this direction, which is the dependent or NP part, usually there are some orders. So here you have clearly the linear orders. And even though you don't have here in the language the order, if I take the field of the PI numbers, you can define the variable, and the variable is order. That's why some order occurs there. Okay. And here you have the random graph, which I mentioned yesterday, that it had certain like random-like behavior, and you have pseudo-finite fields, and you can argue that the reason you have pseudo-finite fields in this line is because you have the Bailey graphs that can be defined in finite fields, and they behave like a random graph. Okay. So of course, this is not completely explicitly defined, but it gives us the idea, for example, of certain dichotomy that is going on. Okay. If you are not stable, you probably have an order in between, or you are too random, and there might be like combinations of the two structures that are not being probably in some other talks. This is more or less the same ideas of Christina mentioned yesterday. So she was mentioning rigidity versus homogeneity as a dichotomy, and then there might be structures that are more homogeneous or more rigid, or combinations of the two. That's not quite the same, but it's also certain kind of principle of dichotomy. You have orders, randomness, and anything that goes in between. Good. Okay, so let me now mention this theorem. This is a relatively recent theorem based on all the tools, let's say, but it's relatively recent by Ampere, and he proves the following. So imagine that you have an ultra product of finite structures, okay? And it just so happens that the limit, the ultra product, is strongly minimal. For example, the real numbers as a group, which is the ultra product of these cyclic prime order groups. You take that and you fix one single pseudo-finite cardinality, which is the cardinality of the whole structure. So just as I did here, if this structure has size A1, this has a size A2, and so on, I just take alpha, which is the limit of the sizes. Okay, just fix it. Then what happens? Well, you can actually give a clear description of what are the possible cardinalities of the final sets. What the theorem says is it goes in two parts. So let me explain the first part. If you have a definable set, you can ask about its non-stable cardinality, and the non-stable cardinality is going to be given by a polynomial with integer coefficients. This is the actual integers. So integer coefficients evaluated in alpha. Not only that, but the degree of the polynomial tells you something about how big your set is. So the Morley rank, because you know what that is, the Morley rank of the final set, which should be a P, is equal to the degree of the polynomial. This is so the size of the definable set in a strongly minimal pseudo-finite structure is given by polynomials with integer coefficients evaluated in one single variable, which is alpha. Okay, cool. Not only that, but you can parameterize the result. If you have one formula, phi xy, notice that with the formula phi xy, you can define many possible definable sets by just varying these parameters. Why, right? So if you have a fixed formula, there are finally many possible polynomials with integer coefficients, and finally many formulas in variables y that tells you precisely which of the sizes you take. Okay, so the idea is this last part over here. The size of the definable set, this depends on n. No? The the size of the final set is precisely the polynomial pi equal to alpha if and only if n satisfies that particular formula that defines the size. Okay, so there is a strong, good description of the cardinalities, and there is the definability conditions of whether these cardinalities may happen. Okay, so well, this is an result. It is this very strong form, and I would like to mention, just because I think, well, not just because of that, but also because it's an result. So these results, as it is stated, was generalized by Alexander Panel last year. Okay, so he proved that any uncountably categorical pseudo-finite structure will have the same behavior with respect to cardinalities of non-standard definable sets. Non-standard cardinalities of definable sets. The only changing here will be that the polynomials do not depend on do not have integer coefficients but rational coefficients. That will be the only change. Otherwise, it's the same variant. And Alex is here, so probably if you want to talk to him about this result, that would be nice. Good. Just as an example to see how this looks like. Imagine that you have this formula, right? You have this formula in the language when you have addition and a zero, and the formula says, well, x is divisible by 2, so there is an element that says equals x, and you have this other bit, which is x plus y1 equals y2, or x is different from y2. Okay, this is a somewhat artificial example. I'm gonna show you why, but it's gonna be important later. So first of all, this theory is known to, this structure is known to have quantified elimination. Okay, which means anything that you can say with quantifiers can be also said without quantifiers. So in particular, remember that from yesterday this group was divisible. So saying that x is divisible by 2 is basically saying that x is in the group. Okay. So this first part of this quantifier is actually not needed. You should focus on the second part. And then the second part, I'm saying, okay, either I'm this guy, because you can take y2 minus y1, or I'm different from this guy. These are the actual dichotomy here. And the possible sizes that this formula can take, depending on how I vary a1, a2, and a3, are either the whole set, because I can say I'm different from A or equal to A, that would be everything, because I believe that P and or not P is the whole thing. And that would be alpha because it's the whole structure, or probably I'm just taking 1 point out. If I'm taking 1 point out, then it's alpha minus 1. Okay, that would be. So two possible sizes. Let's say that the polynomials are x or x minus 1, depending on what are the properties on the parameters. This is how it looks like. Of course, this is a very easy example, but you can make a more difficult one if you take a model of this theory of the R branching tree. You can say, okay, now that I have two variables, I want x1 related with x2 and x2 different from 1. Okay, that's going to give you a different cardinality. If you think a little bit about it, you will notice that this is the cardinality. But I want to point out something here. So these are two variables, so dimension may be 1, 0, 1, or 2. Okay, but the fact that you're saying that the first variable is related with the second one means that once one variable is fixed, the other one has for defining many possible chances. So the dimension should be actually 1. And what you see here is a polynomial evaluated in alpha, and notice that the R is fixed here. So this is a polynomial with integer coefficients of degree 1 because it's defining a set that has dimension 1. That's more thing. Okay, now let's switch gears a little bit. I'm going to show a similar example. What I want to point out is that this is an example. These are results that we got with Melissa Roberts, this thing that I mentioned yesterday. But it's an example that is very similar in nature to the result of Pele, but it's only with a particular kind of response. Okay, so it's not a structural result like the one of Pele that is every strongly minimal structure that does this and that. It's just for this particular example. If we consider this supergroup of graphs such that the girth is going to infinity and the degree are going to infinity, but they are regular, you have a similar thing going on. So you take any infinite product, which is going to be a model of this theory of the infinite branching tree, and you fix this time you don't fix one non-standard integer, but actually two non-standard integers. One is the size of the whole structure, this was before, and the second one is the size of the ball of radius 1. Okay, so this is going to be regular, so the ball is going to have the same size in every point. But once you fix these two numbers, then the rest is the same. For every formula, there are finite many polynomials in two variables, such that no matter what the final set is, it can be written as one of the finite many polynomials evaluated in alpha and beta. Okay. Not only that, but you also have this definability of the cardinalities. You have that there are these finite many formulas that tell you exactly which of the cardinalities should, which of the polynomials should I get. Okay. Just to give you a very easy example, and probably that's why this comes into play. You can have, for example, the formula saying, I mean, I'm using some operation here, but the first one says x is a distance 2 from y1 and distance 3 from y2. Okay, this is the. So the size of that definable set, the size of the elements satisfying that property, well, it depends on what is the distance, the original distance between y1 and y2. For instance, I mean, probably it's easy if I make a picture here, but for example, I have a. It could happen that this distance is 5. 1, 2, 3, 4, 5. Okay? And this is A1 and this is A2. If this is the original configuration, then there is only one element that is a distance 2 from the first one, a distance 3 from the second one, which is this one. That's why you see in the second line, if the distance between the parameters, it should be A1 and 2. If the distance between the parameters is 5, then it's only one element. Okay? What happens if they are very close to each other? If they are distance 2, then if once I am a distance 2 from A2, then and on this side of the tree, I'm going to be a distance 3. So I can just take any possible value here. Well, it's 2 steps, right? Has to be a distance 2. So I have to be somewhere here, a distance 2 from A2, and then we guarantee that I'm a distance 2 from the other one. How many of those elements are? Well, here I have beta minus 1 elements, right? Because this one has beta neighbors, minus 1 neighbors, minus 1. Each of them have beta minus 1 neighbors. That will agree. So the total size here will be beta minus 1 squared, which I hope is exactly what I wrote. Excellent. Good. Right? So, and the other cases, what happens is that probably A1 and A2 are too far away to have a neighbor that is close, or just the distance doesn't match. Like if you have A1 and A2 at distance 2, there is nothing that is at distance 3 from one and 2 from the other. Okay, this is kind of the point. And of course, look, at this possible cardinalities, I'm only using beta. But if I take the negation, then the alpha starts coming into place. Okay. And just to mention this example, because it's very similar to the previous one, so I took the same formula that I was mentioning in the previous slide, this one. It's the same formula, and the polynomial is going to be precisely the same. It's just changing the r's by beta, so it's one thing should be done. Okay. And you see the polynomial in two variables going on. The dimension of this definable set it will be a little bit weird because before I was measuring a natural number dimension. So in this case, what happens is that in this universe of the infinity tree, what you see is one point, usually many things. These are beta many. If I take here, they are around beta squared and so on. So the asymptotics go this way. But there is a much bigger cardinality, which is alpha, that is bigger than beta to the n for every n. Okay. So this kind of behavior will happen in structures that have infinite dimensions. Say, in this case, the Morley rank is omega. Okay. And because the Morley rank is omega, if I want to coordinatize, I need something that is Morley rank omega and something that is Morley rank 1. And with the one of Morley rank 1, I can coordinatize the rest. Okay. That's what is going behind the scenes in this kind of structure. It's not a general term, and we are looking for a general term of the sort. Okay. How much time do you have? 5 minutes. Good. So I guess in that case, and because I know this definition may be a little bit weird, probably I want to say just definition, the idea of it, and I'm going to remind you tomorrow anyway. So this is a definition that is probably the consolidation of several definitions throughout many years. Right now, the definition appears in the work of C.P. Armstrong, Douglas McPherson, Charles Stein, and Ben Wolf. And it's about going back to the final structure. So we know more or less what we want in the infinite structure, this kind of nice descriptions of definable sets. of cardinalities of the final sets. How does that look like in the final structures? So imagine that I have a class of finite structures. I'm going to fix R. This R is not going to be relevant, and I'm going to tell you later why, but for the moment it is fixed. And then we say that C is a multi-dimensional asymptotic class, okay, or RMAC, if more or less the same behavior that I described before happens now. So for every formula, there are finally many possible sizes. That's why these are functions that go from the structure to the real numbers. And finally many formulas such that what the line says here is that the size of 5 and 8 is approximately this size, with some possible error that is going to 0 as n goes to infinity. Okay, so there is like a finite possible cardinalities with certain error terms, doesn't matter, and that's a multidimensional asymptotic class. And if you want it to be exact, is precisely by saying that the cardinality of the structure is one of these functions. Okay, so I'm going to mention these again tomorrow. Let me just give you a couple of examples that satisfy this, because once you see the definition, you basically think, I mean, there are no examples of this or whatever. Well, the class of finite fields is a famous example that has this property. It's not easy to prove. It's based on work of Chelsea and McIntyre, and it's also based on certain line-weight estimates that people in algebra geometry finite fields and also number use. The Bailey graphs, because of the black box example that I was mentioning yesterday, is going to have this kind of properties. And there are many more, among which we can include this class of graphs that I was mentioning yesterday and also today. If you have a class of finite graphs such that the graphs are regular, the degree is going to infinity, and the curve is also going to infinity, that's going to be an exact class. Okay? But let me just tell you a little bit about this tomorrow in a little bit more detail. And yeah, let me just finish with these references for today and proceed to work. Thanks.
Are there any questions, Dario?
Okay, so you know this RAC applied? Does that imply any nice stability things that can be simple with
I think
regular types or yeah.
means you mean the multidimensional asymptotic classes.
The RAC.
Yeah.
Does that imply being simple?
Yeah, for a minute. I just lose control of this, so I cannot tell you with the slides. We're going to see tomorrow that if you take an autograph of a multidimensional asymptotic class, right? In generality, that's NSOP. Okay. However, this is probably good to say now, there are like one-dimensional asymptotic class which are whose superproducts are super simple of rank 1, n-dimensional asymptotic classes whose superproducts are super simple of rank less than n, and so on. So there are like various levels of how much super simplicity you can have. Okay. In the general case, when R is arbitrary, you get NSOP for sure. Okay. And that's about the asymptotic classes. But about the exact classes, it is actually not known. It's a conjecture of mine. I'm not sure how to prove it, or I don't have any idea of how to prove it. That the exact classes are precisely the ones that are stable. That's what I think. So if you have an multidimensional exact class, the autoproducts should be stable, and vice versa. If you have an asymptotic class whose autoproducts are all stable, I think it's because it is exact. That's just because I believe strongly in this philosophy of there is some randomness. Randomness should be asymptotic, not exact, and randomness means you are stable, not simple, not stable. Okay. All the examples point out that for that to be true, but I have no proof or no idea of that.
And then does the order divided groups classes and fine? Well, no. I'm sorry.
Yeah, once you have the order, then something can happen there. However, it's weird because I mean you cannot have a finite order group, right? Linearly ordered group. But you can have a million groups that have a linear order that looks weird. Okay? Because you will have torsion, but still you can have a linear order. So they don't interact with each other very well, but they're nice examples of what I call order asymptotic classes, in case you want to know. So there is some asymptotic behavior there, it's just not because it's not a probability group, it will not be that algebraically interesting intuition.
Any other questions? Maybe we'll see you tomorrow. Okay, so let's say 5 minutes before we start.
My guess is that
welcome everybody. So we continue with the second talk today. So the next tutorial is by Linda Westrick. Linda got her PhD in the University of California, Berkeley, in 2014. He then did a postdoc in Connecticut and a year in New Zealand in between. And since 2018, she's at Penn State University. She was in computer theory. This tutorial is going to be on Borel sets and reverse mathematics.
Good morning. So I want to start out by just saying thank you to the organizers for inviting me. It's a beautiful country. It's an honor and a pleasure to be here to this tutorial. So the work that I'm going to talk about over the next few days is joint with several people, and I'll specify that when it comes up. But for the first talk today, actually it's more of a background. Right, so just an overview of the topics that we'll see in this tutorial. So today I'm going to introduce many questions related to Borel sets, measure, and category. And I'll introduce all of these concepts. And the entire goal for part one is just to motivate the question that I want to ask. Part two is going to be about reverse mathematics, which is a computability theory or framework in which one can try to answer these kinds of questions. And then in part three, I'll explain what's been so far. Right, so today we'll talk first a motivating example called the prisoner hat problem. Introduce Borel sets, measure, and category, get to the first questions that I mentioned. And then from the field of Borel combinatorics, we'll end up with many more questions. And then time permitting, we can begin to talk about how we might use computability theory in attempt to answer these. All right, so to start us off, let's just suppose that we have 6 prisoners. I don't know why they're prisoners, but for some reason these problems are always phrased in that way. So suppose we have 6 prisoners, they're all standing in a line, so the one in the back can see all of them, but the one in the front can't see anything. And they're all wearing hats, and their hats can be either red or blue. And so here is sort of an attempt to visualize the prisoners and what they can see, right? So there's the one wearing a blue hat, and he cannot see this hat, but he sees all the other hats. And so then they're just trying to guess what color hat they have. And you start from the back. So this one tries to guess the hat. And of course, there's no reason, like he has no information about the color of this hat, so he's probably wrong. But then this one can hear what that one said, and maybe now she can guess correctly that her hat is blue. Maybe. All right, so the game is now that every prisoner is trying to guess the color of his or her own hat, and they win the game if they make at most one mistake. And of course, the first one, sort of without loss of generality, will probably make a mistake. It's really about the rest of them. I have to get it exactly right. All right, so is there some strategy? They're allowed to talk beforehand and come up with some strategy. So let's say that they do that. Can they win? It turns out that they can, but it's kind of a fun puzzle if you have not seen it before. And I don't need the answer for talk, so I won't spoil it. But if you want to think about how prisoners can do that, it's fun to do. All right, so now instead of just finitely many prisoners, let's suppose that we have actually omega chain of them. And the game is the same. All right, so now it seems almost impossible. And yet, remarkably, if the prisoners are allowed to use the axiom of choice when they confer with each other beforehand, then in fact, they can split. And again, it's a bit fun to think about how this might be, so I won't tell you, although if you pay close attention for the rest of this talk, you will find some clue about how the axiom of choice could begin to help to provide such a strategy. Okay, but a strategy that uses the axiom of choice in some way is not very scientific. So I hear the laughter, right? When people are, they're going to confer beforehand and use the axiom of choice. What does that mean? What are they really going to do? What we'd really like would be for the prisoners to have a strategy that we could actually understand. So I'm going to propose that what we should consider a strategy that we could actually understand as what's called a moral strategy. So let's take a moment to just formalize like what we mean by a strategy that the prisoners might have. So here we have R and B for red and blue. Red and blue to the less than omega are just finite strings of guesses that a prisoner could potentially hear behind them before they have to go. And then we can also have sequences of infinite strings of RCBs, which are the basically what a prisoner could see ahead. And so if we take the space of all possible finitely many previous things that somebody could have heard across these sort of infinite sequences of things that somebody could have seen, then if we just take some subset of that space, and I've named that subset by a curly R to suggest the idea of red, that's the subset of situations in which the strategy is going to tell the prisoner, let's answer red. And anything that's not in that set, that's the set of situations where the prisoner encounters that situation. The strategy tells them, let's answer blue. So we assume that each prisoner knows like where they are in the line. Okay. All right, so here for one example, so the prisoner knows that they are, prisoner number 4. So they hear this sigma from the first space, they see this S from the second space, and then they just look at that pair, sigma S, and if it's in the red set, they answer red, and otherwise they answer green. Okay, so there's our strategy. So these strategies live in a sort of a topological space. And because of that, we can sort of define the topology of the space of strategies by considering basic open strategies. This could be like a very silly strategy that somebody, probably not very successful for the game, but just to help organize the space. Consider the set of strategies. So here's like sigma, which represents some things that you might have heard before you. This asterisk represents, all right, here's where you are. And then tau represents some like initial segment of hats that you might see in front of you. And so this set then is sort of comprises all of the situations where you've heard sigma and then you've seen something that begins with tau. All right, so this notation here just means that tau, the finite string, I guess, is an initial segment of the infinite sequence of hats that you see. All right, and what this very simple strategy means is just guess red if and only if what you heard was sigma and what you see begins with tau. Right. So not likely to be a very successful strategy, but we can use strategies like this and combine them to form the class of Borel strategies, which are defined inductively by these basic open strategies are Borel. Taking a complement to that is also Borel. And anytime that you want to take countable intersections or countable unions, this is permitted also. So the purpose of this is that Borel strategies intuitively, they're ones that you can give an explicit definition for what the strategy is doing. So for example, let's say that I start out with my strategy is going to be obtained by taking a countable union, so union over all things that you could possibly hear, of this open set. And so this is the open set of, you hear anything at all, and then you hear red, and now it's your turn. So if this is your strategy, then this is the strategy, guess red, if and only if the prisoner just behind you also guessed red. All right, so again, probably not a very successful strategy, but it has an explicit definition. All right, the Borel sets, of course, are defined like in a more general context as well. So if you have any topological space, and here's just a few, this is really as much for notation as anything. I put these examples up here, the topological spaces I'm going to most often use in this tutorial. You'll see later a lot of 2 to the omega, which is just infinite sequences of zeros and ones, and this notation right here tells us that open set of those collection of infinite sequences that begins with sigma. All right, and in this more general case, you also define Borel sets in the same. All right, so I mentioned Borel sets intuitively, the ones that we described. Just one more quick example of that. That example is the set of rational numbers as a subset of the real numbers. So that's one where, let's say that we start with a description of the rational numbers. You're rational if there's a pair of natural numbers such that you are a fraction of them. Okay, I didn't write, or you're the negative fraction of them. Of course, that's also a possibility. But just to unclutter the slide, I didn't write that one. So if you take this and just decompose it a little bit, then you're saying that there are 2 natural numbers such that no matter what k you choose, which we're going to turn that into a 1 over k to make a little epsilon here, x is always within 1 over k of that fraction made by that pair. So the purpose of writing it in this way is that here, now I've got in the matrix of the formula, actually a statement about open sets. And then in the usual way, we can translate anytime that we have some alternation of quantifiers, that can be translated into intersection and union. And so we get that Q is the union over all pairs of natural numbers of the intersection over all natural numbers of these particular open sets. And so therefore, from the description of how you got the rational numbers, you came up with this way of representing them as a Borel set. Okay, so from now on, anytime that I say Borel, you just want to think, all right, well, we know 2 things about it. One, it's built up by the countable intersections and unions, and then number 2, that it's just something that you can kind of describe what's going on. All right, so theorem. There actually is no Borel winning strategy for the prisoners in the prisoner outcome. And this follows basically from 2 facts about the situation. So the first fact is that Borel sets are measurable. Roughly speaking, they have a well-defined size. So for example, the whole space of possible things that prisoner 0 could see, we could say has measure 1. The whole space of things the first prisoner can see that starts with 0, or starts with R. I think what I meant right here. Could have measure 1/2. The ones that start with blue could have measure 1/2. Okay, but you can sort of inductively take this concept up to all Borel sets. And then there's a fact about measurable sets, which is that they are kind of clumpy, right? So this is the Lebesgue density property. And I'm stating it here for our particular example, and it's true more generally. Anytime that you have a measurable subset of the things that the 0 prisoner can see, as long as the measure is not 0, so as long as in terms of this like notion of size, as long as there's something there, then in fact, there is a clumpiness, there is some strength that prisoner 0 could see, so that for 99% of the different ways that that string could be continued, prisoner 0 will actually answer red. So basically, if you see that initial segment, no matter what else happens, with very few exceptions, we'll say red. All right. So based on these 2 properties measured, I can show you why prisoners do not have any Borel winning strategies in this game. So, proof by contradiction, suppose that there were a Borel winning strategy for the prisoners. Well, every Borel set is is measurable. That was something, that's just the fact that I stated from previous slide, though. There's some proof there, of course. And then the other fact that I stated from the previous slide, that measurable sets have this clumpiness property. So I'm assuming here without loss of generality that the R set has positive measure. If it's not, if it doesn't, then just look at its complement with the set and do the same thing on that. So R is measurable, let's assume it has a positive measure, R is measurable and has a positive measure, then there is some initial segment of what prisoner 0 sees that will cause prisoner 0 to say red 99% of the time. All right, well, that means that you're going to have, if prisoner 0 starts out by seeing tau and then sees R, or starts out by seeing tau and then sees blue, there's going to have to be some like continuation S prime of what the prisoner can see, such that prisoner 0 is going to stay red in both cases, right? Just because if any time that you say red on something that looks like this, if you say blue on something that looks like that, then you're basically saying red and blue like half and half. And you're not doing that. You're saying red 99% of the time. So there's going to have to be some S prime where prisoner 0 actually says red in both of these situations. All right. Well, so let's take those two sequences of what the hacks could be. So first of all, prisoner 0 we know is going to say red if prisoner 0 starts out by seeing tau. So let's start out our two hatch situations by saying prisoner 0 is going to have a hat blue. So prisoner 0 is going to be wrong. So that's going to be the one wrong third on hat. And then prisoner 0 is going to see this tau. And then either there could be a red next and then this S prime, or the same thing, but there could be a blue in that relation. Okay, right. So prisoner 0 is wrong on both of these sequences. Prisoner 0 is saying red, the first hat is blue. So that means that prisoners 1 through tau, if as we're assuming it really is a winning strategy, the prisoners 1 through tau actually have to get it right every time. So they have to say all of the bits of tau. And now prisoner tau plus 1 comes up. And it's a problem, right? Because what did prisoner tau plus 1 hear? Well, it heard blue from the prisoner 0, and then it heard all the sequence from tau, which is correct. And what it's seeing is this S prime. And prisoner tau plus 1, no matter whether we are looking at this or that, is seeing the same thing and hearing the same thing. So that prisoner will follow the strategy, but in at least one case, the strategy will not lead to the correct answer. And so that's it. So it's a proof by contradiction showing that there's no Burrell winning strategy for these prisoners. All right. So this is one proof of that fact. I want to show you now another of the same fact, but using sort of some kind of different notional functions, right? So the reason that this proof worked, right, was because we assumed without stating it that we picked whatever color was being used with positive measure, and then we used the clumpiness in order to get this combination here. So that positive measure is sort of a notion of largeness, so there was a place where it was answering mostly good. So we can do a very similar thing, but using another notion called category. So suppose that I've got some topological space. So a reminder set, a subset of that topological space is called dense if it intersects every open set. And we can think of a set that's both dense and open as being a large set. We're going to call a set cometer if there is a whole infinite sequence of dense open sets, so that the intersection of all of them is contained in A. So the intuition behind this is, so suppose you have one open dense set. For some reason that's sort of has largeness to it. If you intersect two of those together, then you'll still have a dense open set, so that largeness was maintained. If you intersect countably many of those together, well, you may not end up with an open set anymore, but you will end up with a set that is still, in some sense, large. And so we call sets like that, and any sets containing sets like that, coherer. And the important property of them is that if we take a countable intersection of such sets, then of course we're just throwing countably more like open sets into this. The countable intersection of coherer sets remains cometer. So that's sort of where that large distortion comes from. And just by vocabulary, of course, you can tell historically which word came first. The complement of a cometer sets called meter. All right, so if we look at a subset of a topological space, then that subset has we say that subset has the property of pair if there's some open set that does a very good job of approximating the given set. And doing a very good job of approximating the given set means that the open set and the set that we're talking about should agree on a cometer set. Right? So the set B may not be open, of course, it doesn't agree with you everywhere, but the set of locations where it agrees with you is large. All right, and then we have two facts about Borel sets, or one fact about Borel sets, excuse me, and one fact about sets that have the property of pair. And they're analogous to the previous. So it's a fact that I'll talk a little bit about the proof a bit later, that every Borel set has the property of pair. And then a fact about sets that have the property of pair, again, more general, but here stated in the prisoner context, is that if you have a set that has the property of pair, then as long as it's not meter, then there is some more generally open set, in this case, some initial segment of things that prisoner 0 can see, so that if you look at all of the continuations of that thing where you guess red, then that is cometer when considered just as a subset of everything that began with that. Right. So in other words, it's just like the measure fact, right? But it's saying that if you have a property of pair and you're not metered, then you're clumpy in a different way. There's some open set where in that open set, like within that open set, on a large number of possible continuations, you're saying right. All right, so here is a proof of the same theorem. And it should look very similar to the one that you just saw. There's actually only two changes made, and changes that are made are very bold, which is instead of assuming that every Borel set is measurable, we're assuming every Borel set is the property of pair, so going from Borel to having the Baire property. And then because we have the Baire property, we know there's some initial segment of things that this is where you can see that causes her to say almost all of the time. And then you just do exactly the same thing. All right, so here's the first question. Are these different proofs? As stated, it's really just a philosophical question at this point, right? You could say, like, whatever criteria you want to apply to say if they're safe or different. That's sort of a kind of question that I want to bring onto the table at this point. All right, so keep that question in mind. I want to switch topics, but actually not really switch topics, as I'll try to convince you shortly. So, well, on the previous tutorial, we probably don't need these definitions, but I'll just mention, recall a graph as a set of vertices and edges. I'm always going to use undirected graphs instead of edges symmetric. And a k coloring of a graph is just a function that assigns a color to every vertex in such a way that if two vertices share an edge, they should have different colors. All right, and it's a well-known fact that every graph with no odd cycles has a true color. And the proof is very simple. In every connected component of the graph, pick a place to start. Color that one red. Color all of its neighbors blue. Color all of the neighbors red. And just keep doing that. There's no odd cycles, so you'll never run into any problem that gives you a true coloring of the graph. On the surface, a very simple proof, but there's actually a hidden use of the axiom of choice in what I said, which is right at the beginning when I said every connected component, pick a place to start. That's the axiom of choice. And for this situation, you want to imagine that the graph has like many connected components. So like imagine it's not a countable graph. Like it's a graph with a set of vertices is really. So the question of picking a place to start is actually a non-trivial one. So a question that is, could this be avoided? You know, can we two-color graphs without this totally non-constructive thing? All right, so a graph is called Borel if the set of edges is a Borel subset of the vertices across the vertices. And a K coloring of a graph is Borel if for every eye, we look at the set of vertices that were colored eye, that set is a Borel set. And again, we're thinking of the set of vertices as probably being something like 2 to the omega or something in the unit interval. So it's this enormous set of vertices, and then we're trying to color them in a Borel way. All right, so in fact, there's a Borel graph that has no odd cycles and no Borel two-coloring. And the first example of that is one that you have actually already seen. So let G be the graph. This vertex set is all infinite sequences of reds and blues. And two vertices will be called neighbors, or two vertices share an edge, if they differ in exactly one place. So what we have essentially argued in the first part of the talk is if the prisoners have a winning strategy, then what player 0 does, right? So player 0 sees something, like sees a vertex of this graph, and then in response to seeing that, prisoner 0 says something, says either red or blue. So prisoner 0 is actually coloring this graph. What we have seen in both of the previous arguments is two different arguments showing that what prisoner 0 does has to be a two-coloring of the graph in order for the prisoners to have any chance of winning. Right? Because the situation that we created to show that there could be no Borel solution to that was basically saying, okay, well, if there are two sequences of paths that differ in exactly one place, so they're sharing an edge now. But if prisoner 0 says red on both of them, then the strategy gets messed up. All right, so we've already seen secretly one example of a graph that we know there won't be any Borel way to two-color it. That was actually how we found this had no winning strategy. And we showed it via both measure and category type of arguments. All right, and I'm going to show you just one more example of a similar situation, which is maybe more like mathematical example, maybe versus more computer science. So let's take the unit circle and take an irrational rotation of the unit circle. And now let's make a graph whose vertices are all the elements of the unit circle. And two of those vertices will share an edge if you can get from one to the other by a single application of either this irrational rotation or its inverse. Okay, so this is a lovely Borel graph. It's easily describable what the condition is for the two edges to be connected, and it's got no odd cycles. In fact, it's got no cycles at all because the rotation is irrational. So we just have these Z chains. Every connection point just looks like a copy of Z essentially. And why we know that there can be no Borel two-coloring of this? Well, suppose we did have a Borel two-coloring. Well, if it were Borel, it would be measurable. If it were measurable, then there would be some interval in that unit circle that 99% of the vertices from that interval were colored red. Since the rotation is irrational, there is some odd number, so that if you take that interval and rotate it around an odd number of times, it will line up, not exactly, but very close with the interval that you started with. And then everybody that is in this intersection, there's going to be a wrong color because you've moved an odd number of times, but you've gotten back to the same color again. Okay, so this proof has a very similar flavor to the proof we just saw. And it's a proof that you measure, but you can also do almost the exact same thing using a category. Here's another example of a problem from descriptive combinatorics. So Hall's theorem states that anytime that we have, first of all, so if G is a graph, then perfect matching of G is just a subset of the set of edges of G. With the property that every vertex of G is in the endpoint of exactly one of those things, right? So you're just picking a subset of the edges in such a way that every vertex in the graph gets used exactly once among all of those edges. Also, a definition of graph is n regular. Every vertex in the graph has exactly n neighbors in the graph. All right, so almost 100 years ago, Hall showed that every n-regular graph that has no log cycles has one of these perfect matches. Right, so technically he showed it for finite graphs, but it's not too hard to see by some kind of compactness argument that for infinite graphs, this is also. However, if you look at the proof of that theorem, once again, it's sort of the natural way to do it is within each connected component, pick a place to start, and then do some more complicated stuff, like to find the matching. So, but it has this pick a place to start property. So, so people were wondering for some time about the Borel status of this question. So, suppose that you have start out with a graph that has a Borel description, and you always find a Borel perfect matching. And Andrew Marks in 2016 actually showed that you can't necessarily do that. So we constructed examples of Borel and regular, even acyclic graphs with the property that they have no Borel perfect matching. And this proof made a bit of a splash because not only was it a problem people wanted to know, but the proof of that theorem used Borel determinacy, which I won't define in this talk, but it's actually just a really huge hammer. It's not a measure, it's not a category or anything. And in this field of like trying to figure out Borel solutions and stuff, measuring category, we're really the bread and butter of how the proofs like usually go. So we can then use this big hammer Borel determinacy, but it sort of wasn't satisfying the way. It's like, oh, this isn't how these proofs in this area usually go. So he was asking like from that time, hey, can you prove this in your measure? And actually, very recently, somebody did. Quinn just last year came up with a pretty regular acyclic Borel graph that, in fact, doesn't even have a measurable Borel perfect match. And that follows the usual patterns, right? So in this example, and also in the prisoner hat example, the strategy really to show that something doesn't have a Borel coloring is to show that it does not have a measurable coloring, or to show that it does not have a coloring that has the property. All right, so Andrew was asking if you can do it measurable. Turns out that you can. A question that one could also be curious about is there any way to prove Mark's theorem in a category? And that was a theorem, that was a question that he actually wasn't asking as much because very shortly after this result, he and Colleen Miller were able to show that there's some sense in which there's no hope of proving this result using category, at least if you try to prove it using the usual recipe. Right? So the usual recipe for proving that there's no Borel something going on in the category, the usual recipe is show that there's nothing with the property of air that can do it. But in fact, what was known is that anytime that you have a graph that satisfies the hypotheses of this theorem, you can always find a perfect matching that has the property of air. Right, so the usual recipe at least won't work. However, the possibility there still remains, there still remains the potential that there could be some way to use category to prove this Marx theorem. But if there is, then it just couldn't be the usual, like sort of most straightforward way of just showing that there's no perfect matching with the property of air. So here's another example as well, perhaps even more interesting one. So Brooks in 1941 showed that anytime that you have a graph with each vertex has to create most n, but there's no n click, then there is an n coloring of G. again, showed for finite graphs, but you can do some kind of compactness thing and find it's true for infinite graphs as well. So in the same paper, Marx used Borel determinacy again to show that this theorem of Brooks fails in the Borel context. So there are Borel and regular acyclic graphs that cannot be n-colored in a Borel way. Right? So here the hypothesis from Brooks was just that it had no n-click, right? But he's even able to make a graph that just doesn't have like any cycle whatsoever. So it's sort of a much stronger hypothesis. And it cannot be n-colored in any Borel way. But in this case, they were able to very quickly rule out proofs by measure or category, at least if those proofs proceeded in the usual fashion. Right? Because they showed that anytime that you have a Borel and regular acyclic graph, you can always find a measurable n-coloring. You can always find an n-coloring that has the property of there. All right, so the question now that I want to ask is, all right, the usual methods to measure and category did not work, but is there any way using measure or category to prove these theorems? Here's another example. This one is Antonio. I'm going to skip this example for the moment and come back to it possibly if there's time. It's just another example of this phenomenon where we have like a categoric proof of something and you don't have a measurement. Could there be one? I don't know. Okay, so so collecting up the two questions that we have so far, kind of a vague philosophical question. Are similar looking proofs by measure and category actually different, whatever you want that to mean? But it's a slightly more concrete question. Can certain theorems of Borel combinatorics be proved by measure or category? And I say that that question is more concrete, at least because if somebody comes along with a proof of one of these theorems that uses measure or category, it would be one of those like you know it when you see it kind of things possibly. Like, here's some proof by category, we saw it. Now we're looking for some proof by measure, we don't see it. So what I want to do in the next 2 parts of the tutorial is to introduce a framework called reverse mathematics that's going to allow us to formalize these questions. But as a warm-up for that, I want to start by just looking into what kind of computational power these questions actually require in order to solve them. Right? So one way to maybe distinguish between whether 2 proofs are the same is to look at if you wanted to go through and be like super specific about like every item that appeared like in the course of the proof, what kind of computational strength would you need in order to do that? And if you would need sort of different kinds of computational power to do one than the other, then that would maybe suggest that different things are going on. Okay, so I don't assume that everybody is given capabilities, so just to introduce these notions. So we'll say that, so we got an infinite sequences of zeros and ones. So we'll say such infinite sequence is computable. There's an algorithm which on input n, does some stuff, and then eventually outputs the nth bit of that sequence. And a really important observation about algorithms is there are only countably many of them. So you think of an algorithm that's something that's written in your favorite programming language. There's only finitely many letters that you can use and sort of put them together in a finite way. So there's only finitely many sequences that could be computable. There is at least one non-computable sequence. And a typical one, the first one we usually come across, is the halting set. So this non-computable So if I have an infinite sequence of zeros and ones, I can also identify that with a subset of the natural numbers, namely the subset on which the infinite sequence has a 1. And so the halting set is actually represented in that set kind of way. So the halting set will be the infinite sequence that puts a 1 on bit n if and only if the n algorithm halts on input n. Right, and so there's some diagonalization argument you can show this is like a nice example of a non-computable set. So it's also possible to allow algorithm access to an oracle. So allowing an algorithm access to a wide oracle just means the algorithm can go along with the usual algorithm kind of things, but every once in a while, if it wants to, it can ask, hey, what's the nth bit of y? What's the 20th bit of y? Look at an answer. It can use that in its algorithm. Right, so that's an oracle algorithm. then if using y as an oracle, you can compute c plus x, then we'll say that x is Turing reducible to y, or y is Turing above x. So this halting set, so if we use a y oracle, we use an oracle, so maybe we can get more power, right? For example, maybe we could use as an oracle the halting set itself. So then we'd be able to compute the halting set if we had that oracle, we could just ask it, like the questions. But even with some oracle, like the halting set, there's still only countably many algorithms that we can use with it. So there's still, relative to any given oracle, there's still going to be non-computable stuff. And one particular non-computable thing you can get relative to any oracle is the halting set relative to that. So for any x, we say x jump is the set of n, such as using oracle x, the n algorithm halts at the end, like x using x oracle algorithm halts at input end. Right, and then the important fact is that for any x, if you have the jump of x, you can compute x, but not vice versa. It always ends up straight. All right, so I want to use computability to put a kind of a gauge on how difficult it might be to come up with some of the objects that appear in these groups. So I want to look at the bare category part. So I want to show you an example of a closed set that has a difficult open approximation. Right. So remember the set has the property of bare. Remember what that means is there's an open set such that the set in question and that open set agree almost everything. So what we want to do now is say, all right, suppose that we have an algorithm that's going to have access to some open set. And then it's going to try to come up, or excuse me, it's going to have access to some sort of closed set. And then it's going to try to come up with an open set that approximates it. How difficult in terms of the computational power might it be in order to do this test? Well, let me show you an example to show that you cannot always do it computably. And in fact, you're going to maybe need to use a jump in order to get out of approximation to a closed set. Okay, so for algorithmic purposes, if we want to define an open subset, let's say for rationals, the open set can just be represented by an infinite sequence of pairs of rationals. So we can say, okay, if this Q1 is subset of my Q, P2, Q2, etc. So you just take the union of all of those. Right, so that's like an algorithmic representation of an open set. And if you want to represent a closed set in such a way that an algorithm can talk to it, well, you can just give it a name for an open set like this, and then tell the algorithm, okay, but it's actually the complement of that. All right, so I want to make this particular open set, which is basically, I'm going to go and look through all numbers, and any number that is in the halting set, I'll add this interval associated to that number into an open set. And any n that's not in the halting set, it just won't be there. All right, so just imagine we've taken the unit interval, we've just divided it up into infinitely many pieces, and then I'm making an open set u, which is, all right, just put in the nth piece anytime that n enters the halting set. Okay, so this u, it's an open set, and it has a very nice computable name, right? So we're not going to need any extra computational power to name this set because there's an algorithm that all it does is it just simultaneously runs all the algorithms. So it just takes turns, right? Run algorithm 1 for a little while, run algorithm 2 for a little while, go back to algorithm 1 for a little, now to algorithm 3, etc. So you're running all the algorithms simultaneously. And anytime that you happen to see that the nth algorithm halts, then you can just append the associated set to this like growing list of sets that you're using to describe this U. Okay, so this U is a computable open set, and let's consider the closed set, which is a complement of U. So we also don't need any non-computable power to describe this complement set. All right, so here's our closed set, and I claim that this is a closed set where it's difficult to find an open approximation to it. I actually claim any open approximation to this set has to compute the halting set. So let's see why that's true. So just a reminder, here's my definition of set U, here's my set A. So imagine that I do have such open approximation to this set. Well, B has to agree with A on a coherent set. So that means that anytime that I have an n that's actually in the halting set, if I look at the intersection of B with the interval associated to that set, that intersection had better be empty. Because because A has an empty intersection with that set. So we don't want any of our open approximation to happen. And by exactly the same reasoning, anytime that n is not an empty set, if I look at the intersection of the interval associated with n, that had better not be empty. Because in fact, that entire interval is contained in A. So if B is an open set that's trying to approximate A other than with some meager set of errors, then that open set B had better put a bunch of stuff into that. Preferably all of it, but maybe it could get away with slightly less. All right, so any open approximation to A would have to have these two properties. If I have a name for an open set that has those two properties, then I can actually use that name to compute zero jump. So how would we compute zero jump? We would say, all right, I can put in simultaneously do two things. First of all, just be running the right algorithm. If you ever see that it halts them, right, you know that that is an halted set. But simultaneously, you can also just read along the open sets that are contained in B. And what you're searching for is some interval that's intersected the interval associated to n. And if in that enumeration of V you ever find such an interval, then you can actually be confident that n is out of the halted set. Because if n were in, then B would not be able to intersect that interval. Okay, so exactly one of these two things is going to occur. So if you just compute like that, then you'll find one of the two, and as a result, you're computing that halted set. All right, so it's at least if you want to, if you have like some set that's given to you, if you have some open set that's kind of given to you in a computable way, but you want to find an open approximation to its complement, you might need a jump in order to do that. All right, so how does this relate to the question of how much computational know-how is needed in order to actually carry out the proof that every Borel set has the property of pair? All right, so I put up here the proof that every Borel set has the property of pair, or at least a sketch of it. So remember, a set has the property of pair. There's evidence that approximates it, and I'm suppressing in the mention of these open sets that do the intersection. You have to do something with them as well. It's not too hard. All right, so why do we know that every Borel set has the property of pair? Well, remember how Borel sets are defined. They're defined sort of inductively. You start out with open sets and their complements, and then take countable unions, countable intersections. So open sets obviously have the bare property. The open set itself, will work with that. Suppose that I have a set that has the bare property with open approximation U, and I want to show that the complement of that set has the bare property. Well, the complement of that set is going to have an open approximation V, which is basically just the largest open set that's disjoint from U. So this is what the open approximation should be when we take the complement. But as we just saw in the previous example, we might need to do a Turing jump if we're given the set U. We might need a Turing jump in order to find this set U. Right? So this is sort of a part of the proof that if you wanted to do it explicitly, would require you to introduce a computation, something outside of just computation. And then for the countable union, it's simpler. If I have a sequence of open sets, excuse me, a sequence of sets that have the bare property, suppose they have some open approximations. The union of that sequence is going to have the bare property, and the open approximation will simply be just the union of the open approximations to those sets. All right, so this is of course, there's one more thing in the building of a Borel set, which is that you can also take countable intersections. But by De Morgan's law, if you want to take a countable intersection, you can do so using countable union and using some complementation. So actually, these two steps in the inductive proof are enough to establish it for all Borel sets. All right, so what I want us to notice about this proof is that it's an inductive proof, right? It precedes all the structure of the Borel set. So if the Borel set is like really complicated one, like many layers of like intersections and unions, then you may actually have to do this non-computable step many times, and you may have to do it using like non-computable stuff that you got from the previous step. And Borel sets can actually have like a sort of like trans-finite height of, like, if you look at the history of like how a Borel set was constructed, it can have an ordinal height. And so this proves that it's a transfinite reduction, but a single step is not computable. And then you're doing that single non-computable step like potentially like really a lot. So if you wanted to computationally to get a handle on what's going on when you want to show your Borel set is the property here, in general, you could really need like a lot of power. And so that is something that we're gonna get into talking a lot more about next time. I want to draw just one picture. So this is a picture of what happens if we have an intersection, right? So let's say that I have a Borel set that was just made as an intersection of some open sets, B1, B2, B3, etc. I'm going to sort of draw more pictures like this like over time to represent Borel sets and their history of how they're constructed. So if I have an intersection like that, of course I can represent that using Morgan's law as saying, okay, this is going to be the complement of the union of a bunch of sets. And the bunch of sets that it's going to be a union of is the complement of B1, the complement of B2, and so on. So let's say that these open sets of B1 and B2 B3 are computable, so we need nothing historical in order to compute them. Right? Then in order to compute all their complements, we might need zero jump. According to this third bullet point, in order to compute the countable union, we're not going to need any more information. We just sort of take all these open approximations and put them together. But finally, if we want to make an open approximation now to that, we're taking another complement. So we might need zero double jump in order to do that. And this can just go on and on and on. All right, so that's sort of picture of what I'm saying there. Oh, by the way, it says 60, but that's a lie. It's not 60 slides yet. But so just to summarize what we did today. We talked about motivation, prisoner hat problem, and we've used that to introduce the concepts of the Borel set measure and category. We went over the first question, which is about distinguishing proofs by measure and proofs by category. We introduced briefly the field of Borel combinatorics, which is the field of trying to find Borel solutions to graph problems. We found in some cases we were able to prove theorems in that area using measure and category. In some cases it wasn't known whether it could be done. So the main question is, can we say something more about whether that can be done? And we started out looking at the computational approach to how you might, as a first attempt, try to distinguish those. And so here's some references. Thank you for coming to this first part.
To make an historical remark, can you go back to the perfect matrix?
To which slide?
Perfect matrix. Yes. So in the first example of a graph that does not have, so the first example of a graph that does not have a Borel perfect matching, it actually took last collection in the 80s. And it is just the irrational rotation that you just mentioned. It's actually quite easy to see that it does not have a perfect matching. It's for any code to, yeah.
Yes, thank you so much for saying that. I should have mentioned that for the even n, it was known for some time how to do this, and in particular this result that you mentioned. And for the odd n, it was open. And so when Marx showed we're all n greater than or equal to 2, the crucial part was to make it work for the odd. Thank you.
Any other questions?
Yeah, so those are upper bounds, right?
Yes, yes.
You can have a complement can have could not use a parameter.
Yeah. Even in the example that the same kind of example that I did, where you maybe just put in the even, if you just put in like the intervals associated to even n, and left out the intervals associated to odd n. Exactly as you say, you may be able to get away with this, and that's actually really important too.
So many of these proofs use either measure or category or both, sort of basically. Is there any way of characterizing the weight measure and their category as the natural ways to go? I think of, saying, okay, I want a sigma algebra that consists of large sets, so it should be a filter and it should not be contrivial. And if you give enough definitions, you wind up saying, okay, it's got to be either their category or else measure with some particular measure on your intervals.
Yeah, so I don't know anything along those lines, but I think it's a really fascinating question. For us, do you have some other regularity properties, one of them being household convention? So we could ask, could any of these results be proved using that regularity property? Is there some other regularity property that captures like exactly what both measure and category are going to work? But I think there's a universe of questions there, and they're wonderful, but I don't know the answer to any of them.
So just some announcements. There's coffee now, right? But afterwards, these problem sessions will be upstairs in the second floor, right above them. So shouldn't be hard to find. They're marked with the second name on outside, so should be easy to find. Also, the philosophy section has the cancellations today. So they're going to start at 11 with Max Strong's and the other three are.
This is for 0.
Or 1. Count from there. Everyone. I got it clear
No, es que yo creo que